Start, right? Okay, I think it's time we can start. We have about 1 hour, so let's start in time. We do have a folder sharing the Google Doc for the agenda, meeting notes, and our slides, and also links to some notebooks on GitHub. Jean is handing out like a small one page. You can find the link on the one page if you miss the link here. So let me just go ahead with my presentation. So this session is about OpenMindat. So we have 1 hour, and our plan is like this. I will give a very short introduction to what is OpenMindat and then our progress so far. And then Jean, my PhD student, he will give a detailed introduction to the API and how to use it, for example, how to get a token to use the API. And he will also demo a number of use cases in Jupyter Notebooks. And we have 2 guest speakers, Sky Bristol from USGS and Steve Richard from Arizona Geological Survey. They both have used the API for some time in their own work. So they're also going to introduce their experience. Maybe they can also bring some comments and suggestions for the future work of the API. As I said, so we do have the link to the shared folder. We have some handouts. You can pass on this if you want to get the links to the folder and also the slides and the links to the GitHub repository. Okay, let me start. Mindat is a kind of crowdsourcing database. It has been there for almost 25 years. The creator, his name is Julian Raff. Sometimes I feel really jealous on him because I think he takes his interest as his career, his life career. He spent his whole life on this database. It's like his baby. And then, because he put this whole database online in 1999 at the right time. So this database actually built its name and established its name among the communities, including the academia. And so far, you can see it has a lot of records, but the most unique information on this database is the locality and also the mineral occurrence. Basically means in which location a mineral species was discovered on Earth. And that's the most unique information on this database. But it also has a lot of other records like photos and then articles, glossaries, and then about the user community. So far on the website, we have about 70,000 registered users, and about 6,000 of them, we call them as level 2. So they have a right to upload new data records into the database. And there's a team about 60 scientists. Most of them, they are like retired university professors or museum scientists. They help review and clean the uploaded records before putting them to share with the public. It's a really huge database. The user interface looks very simple, but when you dive into it, you will find it's so big. And from outside, we know the details. So the website so far, it has about 17 million pages. And every year it receives about 65 million page views. And the whole database, including the web cache, everything together, is about 27 TB of data. And why OpenMindat? So what I talk is still Mindat. Then what about OpenMindat? In the past 10 or 15 years, Mindat, the technical team of Mindat received a lot of open data requests especially from the academia. You can see a number of papers and the figures in these papers I just shared with you. Because until the OpenMindat project, Mindat has no machine interface to share the data, sets. So every time Julian has to download some data set individually and then share it with the researcher. This is a kind of very tedious work. And then we find, oh, this is a challenge, it's also an opportunity. So 2 years ago, we put together a proposal, send it to NSF and get funded. So the main focus of the proposal is the machine interface. We call it the API, machine interface to Mindat. We do have a framework, but today we're going to focus on the API. Jean will give you more details, but we do have some other plans. For example, we want to leverage a number of existing repositories, trying to enrich the Mindat records. And later, we're also going to build packages in Python and R. And we're also going to collaborate with domain scientists, including, for example, we actually have already collaborated with people at Carnegie Institution, Penn State, to work on some data-driven discoveries in immunology. And this is exactly what I have been doing so far, semantics of some general topics like space, time, minnow name list. And we actually are also working on leveraging schema.log, this kind of easy topic. We also have work on persistent identifiers. Later, I will show you some slides about persistent identifiers. And we will have also implemented some collaborations with stakeholders, especially scientists in immunology. I think in the past couple of days, I have seen a lot of work, presentations, and sessions on persistent identifiers. So here, I also want to share with you, actually, I also want to hear comments from the community about our work. We just established this like 1 or 2 months ago on the Mindat website, and some of this is actually still ongoing when we begin to mint millions of identifiers to the Mindat records. But here is a layout of, I call it the structure of the long form Mindat identifier. You can see example here exactly. Mindat is the namespace prefix, basically HTTPS ://mindat.org. And after that, the first digit is the authority of the identifier. So far, we just use 1 for Mindat. But in our work, we say, oh, maybe we're also going to use some records from other repositories or authorities. So we have this number for representative data repository or communities or associations. And then this one, the second digit here is a data type. And so far, 1 is for, we call it the geomaterial, minerals, rocks, or the variations of the names. And we have a number of them. Like 2 is for locality, and then 3 is for loss entry or the mineral occurrence. And then the last one is actually this one, or not the last one. The second last one is a unique identifier already existed in the Mindat database, like here 337. Actually, it's already used on Mindat as a representation for chords. But by putting this into the long form identifier structure, we don't need to redesign the wheel. So actually, here this identifier is consistent with the existing identification system in Mindat. And the last one is just like a checksum digit. I think it's for version or format control of the identifier. So in this way, you can see from the long form identifier, we can generate a corresponding URL. And on the Mindat website, when you type this URL in a web browser, it will do automatic redirection to the original URL on the Mindat website, and you can see this page. We also have a UUID together with the long form identifier. And then another work, Jean Song will give you more details, is by using that unique Mindat ID, that actually is a part of the long form identifier, like here, 3337. Using that identifier, you can use it as a parameter. Send it to the OpenMindat API, you can actually get, it's not like a page, it's like the JSON code for the actual data set. Here, 3337 is for chords. You can get a long records. I think we have about 100 or around 80 or 100 attributes for the record of chords. As I said, we did carry out a number of collaborations already. Like here, you can see people from Carnegie, Penn State, and a few other universities, Lamont, Columbia. So far, through the support of this project, we have already organized 2 rounds of datathons. I think there are going to be 1 or 2 other rounds before the end of the OpenMindat project. And we've already, it's not only about building the database or enrich the database, we do have the scientific purpose, and we want people to use the database. I think the API is a good way to accelerate that progress. And then here is just another thing. Anyway, the A is offset. IPA. Why? Because when we organized the first datathon, I think it's just by mistake. Julian was intended to see API, but he just said IPA. So let's say, okay, let's use the IPA as the icon for the OpenMindat project. So I just put something together as IPA or API anyway, just to add some fun to the project. Okay, I will end it here. I think next I will ask Jean to come here to introduce the technical details of the API or IPA. Yeah.
Okay, thank you, Marshall.
Yeah.
So today now here I'm about to give a brief and straightforward tutorial for our how to use exactly from scratch, how to gain the access to the API token, and how to get your hands in this API and obtain the exact data set. Sorry.
So actually sharing the screen, I do have a QR code here. It's a link to the Google folder. You can find the slides and also links to the GitHub repo. And I have a few handouts here. If you need the link to the folder, you also can just click it.
This one?
Yeah, I think the technical team, they will receive a message.
Is it downloaded?
I don't think so. I've already have this downloaded, but because we do not have an Adobe Reader,
Oh.
I think that works. Okay, sorry. So when I get everything all set, so today I will give a short presentation about the API tutorial. And as Marshall mentioned, Mindat is a very informative and valuable data source for mineral informations. But originally, you can see the website is designed for human readers and hard for machine to access the data. And that's why Julian and other technical staffs decided to develop this API to process and obtain the data. You can see I just listed a few of available mineral attributes for the mineral species. Actually, they do provide over 100 different mineral attributes for the mineral species, localities, and some rocks and other varieties here. Including, say, the ID, name, chemical formula, and many other physical properties. And to gaining access to this API, we are just one step away from it. You will have to apply for your API token. And first of all, you will need to, and all the process will be for free. You will have to register for one Mindat account and apply to upgrade and activate your account in your homepage. And actually, at this time, we do have a staff called David, who is backing us. If you start to process your application to this API, you will get your application processed very fast. maybe within this hour. And normally you will take 1 to 3 days for the staff to process your application. And keep in mind that after you're applied for your API token, once your application get processed and approved, you won't receive any notification. But you can come to your Mindat account and check the section called edit my page. And if your application get approved, your API token will show at the bottom of this section. And don't worry, I will provide the QR code and the URL to this tutorial at the end of this presentation. So, and I will also provide a temporal token for everyone sitting in this room to do some simple demo after my presentation. So don't worry about this. We can really do some demo in this conference. And I will provide some best practice for this API. Say, the workflow for our API is really simple. It just consists of 3 parts. The first thing is that you have to determine your data endpoint. It's somehow like a knocking exactly the doors for the data repository. Say if you got interest in the geomaterials, which corresponding to the mineral species, the rocks, and the variety for the minerals, you will need to select the geomaterials. And the minerals IMA data endpoint is rather exclusively for the IMA approved mineral species. And also you can access the locality data by using the locality data endpoint. And with your API key put in the header, and param is corresponding to the parameter, which is used for this kind of query functions. You can achieve filtering, selection, omitting, grouping, and apply special flags for your query to access the exactly what you need from OpenMindat API. And here is a data example about what you will get from the query. You can see everything will be put in a well-structured JSON file, which will be very easy for data analysis and further research. And now I will give 2 short brief presentation for the potential application for the API data. You can see that this is a demo to demonstrate the chemical components distribution among all the IMA approved mineral species. It's very intuitive. And another application is that to simply retrieve all the mineral name list, and you can quickly to compare it with other potential mineral data sources such as IMA or RAF database, and you can easily to compare the difference between these different data portals. And I will just skip this part. And now I encourage everyone sitting in this room, you can, by scanning your the QR code, you will direct you to our Google Drive, and you can click in this agenda doc, and just it will direct you to here, a GitHub repository. We can start from this repository and do some simple data demo. How to use Mindat API? As you can see from here, it can direct you to apply for an API token.
Did everyone get to
The yeah.
You need any help?
So anyone need any help can raise your hand. Yes, actually we do have 4 prints for this QR code. You can pass it to others who need these things. Home link. What? The QR code. Maybe I can simply
So the link and handout will guide you to this folder. And then you can just open the Google Doc.
Yes, you can directly use this GitHub. Yes.
Can you open the Google Doc just to show people where to find the link to the GitHub? Yeah.
Yes, it's at the section of agenda. You can scroll down to the page 3, I think.
Yeah.
Page 2 or 3.
Okay, a lot of people are already here.
Yes.
You can go to the Google Doc and you can find the link to the GitHub.
Yes. The GitHub repo, how to use Mindat API. Yes, and normally we will only have 2 ways to access to this tutorial. And this for this conference, we do have a special tutorial for ECIP, which will include a public API token for everyone to do some test. But keep in mind that this token will get invalid after this conference. So I suggest you to apply for your own API token after this conference. And by clicking on this thing, collab for ECIP, it will direct you to a Google Colab folder. As you can see, you can simply run. You can forward the first section called dependencies and click the run button. And
now I'm in live communication with Mindat technical team. And they said he already approved like 3 or 4 new requests. So you can take a look if you already got your own token.
Yes, if you
that
Profile.
page and then token file this for you.
Yes, if you already successfully get your API token, you can find the token at the edit my page and
Go to your profile.
Go to your
and then
profile.
in the menu, there's an icon called edit my page.
Yes.
Just click it, and then a page will pop up. You go to
Yes.
the bottom, you will see your own token for the key.
yes, you can copy and paste your key here. And you don't have to use my key.
Yeah.
At the first section, you
If
can,
don't have one, you can just use keys.
yes, we only have an existing one. And if you have your own one, you can try it and by pasting here. Yes, there is no button called a profile. It's called my homepage. At the upper right to the Mindat, I think.
Click edit my page.
Yes.
Okay, thank you. Okay, got it.
And you can copy and paste to the section 1 dependencies here.
So where next step? Yeah, I could go.
Collab for ECIP at the GitHub repository here in the table, collab for ECIP.
So if you go to the GitHub repo, there's a link to open a notebook and it's showing. Okay. You can run it from there. There's a point where it'll ask for inputs and you can input in copy and paste. So basically it goes to that GitHub repo.
Yes,
There's a link in there to open the notebook in Colab, which will let you run it.
No, I.
It's always thing people are doing, they had a demo.
yes,
Everybody has to get a key.
yes. And well, you can keep the key things after the conference. We can keep going with our tutorial. And actually, I already have all the codes ready in the tutorial. No coding is necessary for this demo. And the dependencies, if you got interest, you can read all of these things. It's just about importing some necessary package from Python and input your API key and you are good to go. And for the use cases, I do have a series of use cases here, including getting the materials by applying different querying strategies, selecting, omitting, and changing the data endpoint. And also you can do some fuzzy search and get the single locality here. Maybe you can start from the first one. Get geomaterial item with select fields. You can see this is a very helpful website for the OpenMindat API documentation. You can see all the corresponding parameters for our API you need in the future if you need to do some deeper analysis here. And for the, but you can see this here are some of the available fields for the mineral species information. But we do not include the corresponding explanation for the fields. But one of our staff have done this very comprehensive explanation document, which can be accessed here. You can check this later. So there are just two blocks of codes here we need. In the beginning, you have to determine which API URL is used. This is a constant URL. You will not need to modify this later. And here, the header is where you can put your API key, which you just define in your first section. And these three lines, line 4 to 6, are just determine what your downloaded dataset will be named and where it will be placed. And after setting this, you can declare that all I need is the field about the mineral ID, the name, and corresponding Mindat formula. And this block of the code is just to let you to set your filtering string to the parameter and determine the format of JSON. And the response, this line will apply all the determined Mindat API URL, which is defined here, api.mindat.org here, and geomaterials is corresponding to the data endpoint, and parameters equals parameters, headers equals headers, and you can start to do the downloading things. Well, you can, don't forget to run this block first, and then the second one. Normally it will take less than 1 second to finish the downloading. You can turn to your left column of files. You can see as here, our downloaded dataset is named Mindat item select.json. You can take a look at here. Maybe you can double click. And as you defined, the ID, the name, and the corresponding Mindat formula are already downloaded. And you may notice that you only have 3 items downloaded to your JSON. That's because to save some time, I managed to comment out the for loop for our data obtaining process. If you uncomment this part of things, it may take around less than 10 minutes for you to obtain the entire mineral data from the Mindat. But to save them, for demo purposes, I decided to comment out the for loop. Therefore, you can only get the first 10 of the mineral species. And in addition, you can try other data blocks, say the omit fields, and I'm approved, and including some locality and some other things. So no coding is necessary. Just run the 2 code blocks for each subsection, and you can see the result. And to see the entire data set, you simply select this part. And if you are using Windows, you can click Control and / to uncomment this block. And if you are using Mac, you can simply use Command plus the / to uncomment all the things, and you're good to go. You can download all the things, but this kind of operation can be time consuming because we do have a lot of data from Mindat. I think that's the demo.
Yeah, any other questions before we move on to the next slide?
Okay, thank you.
Yeah, you can always ask the Jean in this session.
Yes,
You need help to get to the note.
yes, for further tech support, you can see from this agenda, we do provide our, let me see, where? Here,
Yeah,
Any-
my email address.
yes, under this GitHub repo.
All the way up, question, you can always-
Yes,
And also for those really seriously interested user, we do have a Slack channel with the Mindat hack team. So if you like seriously want to continue the usage of Mindat and OpenMindat API, you can send me an email and then I can invite you into the Slack channel. They are very helpful and the people that are very friendly about the reuse and the application of Mindat reports.
They are even willing to accept critique.
Yeah. Okay, thanks, Gene.
Okay,
And,
thank you.
we move on to Sky's talk.
Okay, I'm gonna use my machine and I think I'm shared with people. I think we're good and I'm shared on Zoom, so I think that should be fine. So I'm Sky Bristol. I'm with the US Geological Survey. I am part of what's called our Energy and Minerals Mission Area. And I'm going to share a current use case. In fact, stuff that I'm working through right now, the things that Marshall was showing earlier with the long ID, even this, the API has been a little bit volatile and developing. It's very much beta and has been a little bit for a while. It's starting to stabilize, but the initial run that I did with some of this a number of months ago, I used a different identifier because the long ID wasn't available. So I had to go back in and do some identifier cleanup not too long ago, but things are coming along there. I did drop this particular URL into the agenda notes, and there's also another link in there to a different GitHub repository. This isn't really about a tutorial, but it shares the work that we're doing. There's a lot of stuff in that repo that's associated with the geoscience knowledge base, which is what I'm going to talk about. That's our use case here. I'm kind of trying this idea of using the tool that I'm using to build the tool. So this is the knowledge base itself. It's a Wikibase instance. I put the presentation, I laid it out in here, provided a link to it so you can go back and refer to it later, and we're continuing to build that. And I'm actually just going to walk through a number of things in this particular Wikibase instance based on the work that we're doing to kind of lay that out. So I'm going to give you kind of 4 pieces here, a little bit of the motivation for this, why we're doing this in USGS and kind of what we're doing. I'm going to talk a little bit about what's been done in the past, sort of the history leading toward this and where it's heading for us. I'll talk about how we're representing knowledge in this knowledge graph and in this knowledge graph. And how we're leveraging Mindat then as a source and a connecting point in this particular work that we're doing. So I'm going to walk through those things and kind of give you those pieces. And like I said, there's a lot of links and things to look to there as well. The code that I have pointed to, I'll show that at the end. It's not something that I'm expecting everybody to run, but I actually did set it up to be runnable. You can change the API key in there and execute the functions and do that kind of stuff. And I'll talk through that just a little bit here in just a minute. So I want to start with sort of the big picture here real quick, just to give you more of a sense of what this is all about and how it factors into things that are going on within the USGS. So we're working in energy assessments and mineral resource assessments right now. These are things that are mandated by Congress for the USGS to do around all of the minerals. We have a tremendous amount of work that's going on right now around critical minerals because of all of the importance of them in renewable energy and many industries and things that we're working through right now. So the current process takes a tremendous amount of time. The little workflow that I laid out up here at the top is what our scientists work through. And our current state is a tremendous amount of data wrangling that goes on well before we're able to even begin an assessment. Roughly a year takes place of data wrangling goes on before we even get into the interpretive work right today. So some things need to shift in that. We have laid out a 3-part strategy. I'm really going to talk about one part of that. There's a couple of other pieces that I could talk about in other places, but I'm going to talk about this knowledge banking piece here. And what we're describing is a need to move our whole paradigm from databasing to knowledge banking. Right now we create a bunch of these individual databases that are all sort of disconnected from each other. We sort of know how they connect. We have enough metadata that other people can connect them to sometimes, but that's really not good enough. And we need to move on beyond that particular point if we're ever going to amp up our game in this. I'm happy to jump into more parts of that down the line, but I want to come back to the geoscience knowledge base itself and what this is all about. So we are building this. This is where it is. It lives at geokb.wikibase.cloud. This is wikibase.cloud is a project that's being executed out of Wikimedia Deutschland. It's essentially sitting adjacent to Wikidata. Wikidata, if you don't know what that is, it's part of the Wikiverse. It is essentially the global knowledge commons. It is where communities all around the world, all across different domains, all languages are trying to come together and assemble the world's knowledge of everything. It's a massive lift, and it's kind of crazy. If you get into Wikidata deep enough, there's tremendously wonderful information there, but there are semantic collisions all over the place where people are trying to make sense of what different things actually mean and how they should be discussed. But we're using this partly because it sits there. It sits adjacent to Wikidata. And part of what we're working to do is make sure that we can put our information out, government information out, in a way that can stub in to that world. We're not mucking around in Wikidata, partly because I don't think we want government agents mucking around in the global knowledge commons. But partly because, but we want our information to be integratable into that particular environment. So this platform is here, it's online and it's available, and I'm kind of sharing it here because I am inviting collaboration in this. Part of the beauty of working in this environment is that it's based on MediaWiki, the same environment that we've been using for decades and decades to build information collaboratively in Wikipedia and other places. So this is an open invitation to jump in on this with us and help to move it ahead. So this is not, though, our first foray into this world of putting all of this information together. We've had things in the past that do a lot of this. This is Mr. Data, which is kind of a nice name, but it stands for Mineral Resources Data. This is a system that another brilliant, passionate guy, kind of like Julian Ralph, Peter Schweitzer within the USGS, has built over many decades now as well. It has thousands of data sets and databases within it. It does a lot of the sort of linking and knowledge-based things, but it's not based on a knowledge graph technology. But there's a lot to this in terms of individual data sets and the connections between them, linkages through those based around topical areas such as our science topics, chemical elements and the kinds of things that we were actually just looking at there a minute ago, link into different parts of that system and create interconnections between it. There are whole data systems there, including this legacy data system, MRDS, the Mineral Resources Data System, that go back to decades past when we had the U.S. Bureau of Mines and other things came together. So there's a lot of data that's been brought forward, more from the level of mineral development and mineral prospecting and mines and that sort of thing. What we were looking at earlier with MINDAT specifically in localities has to do with mineralogy and the development of minerals. So the piece of the puzzle that USGS is starting to bring to the table has to do with mineral occurrences, mineral deposits, and mineral deposit developments and mining information that we're working to connect in with MINDAT in a number of different ways. But MRDS and much of it, Mr. Data, is also suffering because it is a one-person passionate project, and it needs to move into the next generation. And that's part of what we're doing with the geoscience knowledge base, is helping to bring some new technologies to that, working to bring all of that data and information into a new framework, a knowledge representation that will hopefully stand the test of time. So we have great historic information here. This is the only operating cobalt mine in the U.S. was operated years ago in Idaho. It's called the Blackbird Mine. A little bit later on in life, it was called Idaho Cobalt. And this is about where things stopped with MRDS, and it's not up to date with a mine that's being operated by an Australian company, Idaho Cobalt Operations now. So many things like this need to be brought forward into the current age and made part of a larger system so that we can really understand what's going on across many of these domains. We've done this kind of thing in other places as well. I was part of building a system called ScienceBase years ago, which is another repository that USGS has. And we had aspirations at that time of building a knowledge base, a knowledge graph out of this, where we would connect everything that we possibly could across all domains in USGS together into one scientific database. We kind of did that, but we kind of have not. Actually, ScienceBase's roots go back to Freebase. I chatted with the Freebase guys in Silicon Valley years ago before they got bought out by Google and became the Google Knowledge Graph, and used that to build much of what was in ScienceBase at the time. But ScienceBase has ended up really focusing on these discrete data sets as a repository for them and serving those up in different ways. But nevertheless, ScienceBase has 17.5 million things in it. There's a lot of stuff there. There are records of everything from data sets to physical samples to projects to maps to many different things. Some of them are slightly connected to each other, but many of them are really just disjoint individual items that you can go to, download a database and do something with at some level. Another activity that's getting a little bit closer to a connected knowledge base that's going on right now is through an activity called the Internet of Water, something that we're doing with many partners, including NOAA and others around the country and around the world. Dave Blodgett, who's very involved in ESIP, is very heavily engaged in the development of something called GeoConnects within that, which is a graph of mostly geospatial features on the hydrographic network that we're trying to deal with. And so they have brought a bunch of technologies together. They've built an RDF capability, a graph capability, and I just lost my ability. Okay, there, sorry. So you can query that using Sparkle, and I'll get back to Sparkle here in just a minute, quite a few more examples of that. Get to kind of all of the connected information essentially associated with stream gauges, associated with other things that are called events on the nation's hydrographic network. So they're doing quite a bit of work in that regard, and it's adjacent to the things that we're doing. And so we're kind of all nudging our way toward building a very large connected knowledge base capability across the sciences in some way. So let me come back to the geoscience knowledge base, and I'm going to dive into sort of where the connections are here to MinDat, how we're going about building those connections. I'll show you the code that we're using to do that, so you've got exposure to that. And then we'll wrap up here in just a couple of minutes. So coming back here to this page, if you browse around in geokb.wikibase.cloud, you'll pretty quickly come across a page like this that says Sparkle examples. This is essentially where we are actively documenting all of the entities that we are beginning to bring together into this system. I think we have 50, 60,000 or something entities in the graph today that we've brought together so far, and then all of the interconnections and everything between those. So it goes through those in a few different sections. You see we're dealing with mineral commodities and mines and mining facilities and rock classification. These are the types of things that we are bringing together into this knowledge base. And some of those we are leveraging essentially from MinDat, because it really is the best available source for us right now to get a hold of these kinds of materials. But I want to walk through a couple of examples of those that we have, just to give you a sense of what's there. Within the system mines, the information about mines is something that we have quite a bit of information on. And we're using the wiki again to kind of capture a little bit of our thinking, a little bit of our discussion about how do we deal with these different kinds of things that we're trying to deal with? What are the questions that we're trying to ask? And with mines, that's one of the big inputs that we have to our mineral resource assessment process, where we need to understand the prospecting history over time. What minerals have been taken from the earth, where, how much is left in different places. These are all inputs that go into our assessment process in different ways. It gets more complicated than that, but at a high level, that's a lot of what we're bringing together. So we want to know these kinds of things. We often have 5, 6, 8 different sources of information about the same mines in different places in these individual discrete databases all over the place, and figuring out how to rectify that and which ones of those records should we choose and what's the best information is often a really difficult process. And what often happens is we do that behind the scenes, and we share a little bit about our judgment calls that were made when we did that. But we don't really expose that judgment. We don't tell people all the time, this is how we made the calls that we did to assemble the best database that we could for this process. And it's also really hard to do that in the current state of this kind of information. So one of the kind of problem areas that we're trying to solve is how can we bring all of these together, all of these sources of information together into one place, store sufficient information about each record and each assertion that we have, including things like where is the mine located and what commodities were mined. I mean, these kind of simple pieces of information often disagree from one data set to the next to the next. And so we need a place to bring all of that together and to surface the different kinds of judgment calls that we need to make when we are analyzing this information and trying to bring it together for use in some way. So that's described in here a little bit. And there's a Sparkle query in here. One of the cool things in Wikibase and MediaWiki is you can kind of actually put your little code in here. Actually, maybe I can make that a little bit bigger. I don't know, now that I'm looking back there. Does that help a little bit? Sure. Bigger. There we go. Maybe that'll get there. Now I won't be able to see it, but that's good. So one of the cool things that we can do is we can, kind of show you how to query. So you're going to start finding these all over our Wikibase instance every time we figure out that, oh, well, this is how you actually query this system. We'll have that. And there's this little try it button down here that brings up a query interface. We can click run and go run this query. And in this particular query, I said, basically, well, give me this example that I just talked about. Show me some mines where there are more than one claim, there's more than one assertion about where the mine is located. So let's go look at one of these. I think there was a coal mine in here that had 7 of these in it. So we'll go pull that one up real quick and take a look. Okay, so this Altoona Coal Mines is a mine. It's also an adit. So it was a hole in the ground someplace in this case, and it had 7 different coordinate locations. One of them came from a system called the Geographic Names Information System, the GNIS. So there's a name out there and it's got a coordinate, but that one's not very good. Most of those coordinates came about because that was the best place to put the label on the map. Not necessarily that was the best place where the mine was, but nevertheless, that was an assertion that was made. But now we have this other system. We have something called US Min. And a bunch of these digitized prospects from US Min, they have different information in them. They have stuff that says, oh, well, here's the coordinate and it's labeled on there as being abandoned at some point. So there was something, here's another coordinate that was there. So what's actually going on here is this is a mine that has multiple features on the landscape that make up the total mining location in some way. But we don't necessarily know that until we start bringing all of that information together into one place and structuring it in a way that we can deal with in some fashion. So that's a lot of what we're working to make our way through. So now let me switch to Mindat real quick and talk about what we are pulling from Mindat. Marshall mentioned the localities as being the really unique piece of information that's here. Well, that's true, but there's also some fantastic reference information available here that is the best available source for this. Gian mentioned the IMA minerals, the International Mineralogical Association minerals. We need to have that list, but it's available in a PDF. Honest to God. And, these guys have spun this stuff up and mobilized the information and made it available through an API that means, hey, we've got a place to go tap that information. They've provided enough detail there that we actually get everything we need as if we'd gone to the IMA for that source. This is just a great mobile source to get a hold of that. It has rock type classification, which also comes from another source. But it's really kind of nicely mobile here, and it's laid out in a way that we can really get at this information and work with it in a number of different ways. So we're pulling that kind of stuff here. So we can go back to our examples and we can scroll down and we can look at our rocks. I pulled up this little use case earlier because one of the other things that I wanted to talk about is when we need to, one of the kind of experiments that we're going through in our geoscience knowledge base right now is looking at places where something is more than one thing. And so here's an example of a query that's looking for commodities where something is actually called more than one thing. So we can pull up something like cobalt, take a look at that. And cobalt as a name is a mineral. It's actually a chemical element in itself. It's a one element mineral and it's a mineral commodity. You can see we've pulled this from Mindat and these Mindat identifiers. Those were those long form identifiers that we were looking at. You see them in our geoscience knowledge base. We pulled that directly from Mindat, and that takes you now right over to Mindat to go look at that core record. So we only pulled a couple pieces of information out of Mindat. There's a lot more depth there, as GN was showing. We've only pulled just a little bit of that stuff back for right now to that's just what we need at the moment. So to wrap up real quick, I'll point you to our repository that's for this geoscience knowledge base work. This is also linked in the agenda that's there. There's a whole bunch of stuff that's here. You're welcome to look through all of these notebooks. I don't suggest you go try to run them. This is work in progress code. I don't have an environment YAML file in here that's going to help you run all of these. We will work on making this better, but this is really work in progress that we're going through. One that I'll highlight here, though, real quick, just to finish up, is WBREF Mindat. That's the notebook that's actually done the work that we were just looking at over there in the in that system. So we've got some notes that are in here. Our stuff is here. There's that whole process that we were dealing with taking care of your API key is handled a little bit differently here than how GN handled it in terms of setting an environment variable, but it does the same sort of thing. You're welcome to go fiddle around with that. The part that I'd point you to is this set of what I call helper functions. These are essentially Python functions that handle the process of going and talking to the Mindat API, paginating through the results that it needs to get through, packaging them up as a data frame in this case, and bringing them back to the user. So if you scroll down here just a little bit, you'll see where that code is run. It's grabbed just a few attributes out of there. And I was really interested to see that fields parameter because I didn't even know that existed. So now that I know that's there, that's really handy. I can ask for just the fields I want because I've had to filter them after the fact. We bring that information back. This query that we're looking at right here, just down below it, that's a query that goes against our geoscience knowledge base using Sparkle to bring back essentially that same information that we dropped over into that particular space. So I know that was dense and quite a bit of stuff to work through, but I wanted to kind of give you the picture of how that's come about and how we're leveraging the heck out of what Mindat provides. It's giving us thousands of things that we really need to have in our environment as well. So thank you.
Thanks a lot, Scott.
May I ask a question?
Yeah, I guess.
So for the USGS, really, Mindat gets you through the IMA minerals list.
Yep.
But for rocks, it gets you through to the, what is it, mixture of IUGS, BGS list. So you happy using that IUGS, BGS list, or you have your own weakness?
What we would dearly love is for Mindat to cite their original story for that and show us the problem where that comes from.
Okay, but there's another demand.
Yeah.
So we're trying to get the IMA and that BGS list onto probably by February.
Yeah.
So that to me would be ideal.
Yeah.
And standardized rock names.
Yeah.
Because
So Leslie, I can also help elaborate, but maybe after the session, okay? Because we have about 5 or 10 minutes. I actually have some updates for you. It's like IUGS, IMA, and then the name list, how to coordinate. And actually, Bob Hazen is leading a mineral informatics working group in IMA now, and they are aware of the situation, like how to provide like a more accessible, not only like a PDF document of the name list, but a kind of machine readable interface to their work. So I do have some updates. I will talk with you. So next, we probably need to move on. We have some kind of limited time. We still have Steve Richard to give us an update about his work using Mindat and also the interactions between Mindat and some other databases, including the Astral Materials database and the EarthScan. Steve?
Muted. And let's see, I'll share my screen.
Oh, we cannot hear you. Are you muted?
I shouldn't be. Oh, I know what the problem is. wrong mic.
Seems
Oh, that's, can you,
still
can,
cannot hear you.
what's going on? Webcam. Hello, testing, 1, 2, 3. Why can't you hear me?
Okay, so volume, I think
Testing, 1, 2, 3. Hello? Check, check, check,
you can see your screen.
check.
but, we cannot hear you.
Can you hear me now? For some reason, the mic's not working. Testing, 1, 2, 3. Is that one working? Fuck. Check, check, check.
Oh my God.
Oh, well. Might as well go ahead.
Also, maybe let's check his microphone source.
Check, check, check. No, my mic is not working.
Oh,
Yes, yeah. Outside. The volume is yeah.
maximum.
No, it's,
Oh my God.
check, check, check. Check, check, check. Any luck?
I think we will have an echo, but problem is we cannot hear.
Okay, I'll try rejoining.
Well, I glossed over.
I think Steve is trying to restart his Zoom.
Yeah, let's see if
He dropped.
He dropped.
Okay. He can hear us.
Some of that we're actually pulling from documents. Exactly. The process of category document process.
Go ahead, no time to debug. Input some slicing folder. Okay,
Can you still hear us, Steve?
Any luck now?
We still cannot hear you.
Okay,
hear it.
There are many different sources.
this one?
The other,
Getting that
yeah, next to the microphone. Yeah,
established
yeah.
with that stuff.
Speaker?
Can we test the,
Claims for assertions of information.
test.
check, check. Is this one working?
This one.
Different sources.
Nope. Hello, okay. Nope, nope.
Okay.
Steve, try again.
Check, check. Hello, hello.
Yep, we
Can you
can
hear
hear
me
you.
now?
Very.
Test.
Hello, 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 hello. No. All right.
So same as.
Can you talk again?
Check, check, check. Hello.
Okay.
That's the audio.
Any luck?
Can hear you through.
Hi, Aaron. Hey, Marshall. Any luck? Nope. Okay. You're out of time, aren't you? Okay. Oh, well. Bummer, bummer, bummer. Testing 1, 2, 3. Can you hear me now? Oh, well. Interesting. I'm not hearing you now. Check, check.
Yeah, you can start now, Steve.
Oh, yeah, can you hear me?
Yep, yeah, good, good.
Okay, disable screen sharing. Got to re-enable the screen sharing.
We can see your screen, Steve.
Okay, nope, still disabled. Anyway, hi, I'm Steve Richard. I'm working with the Astromaterials Data Archive and a couple other projects. Doing a lot of work with over the years with geoscience vocabularies, and always been interested in the mineral vocabulary. So in connection with the Astromaterials system, we wanted to have a vocabulary for all the different kinds of meteorites that people are reporting geochemical data from. And MinDat was an obvious candidate to try to get that information. So, oh, there we go. Okay. So I was glad to find out at the ESIT meeting last summer that the API was becoming accessible. And so my basic question was, so how do I mine all this meteorite data, the meteorite classifications out of MinDat? And the first thing I tried was basically looking at the API. I didn't see any way to get it, so I just went in and copied out the hierarchy of meteorite types from the web pages. There's an example here, and you could paste those in Microsoft Word and get the HTML links that had the MinDat ID numbers in them. And then with a little bit of massaging, I could pull out the MinDat IDs and then plug those into the API and make a request on each ID to get all the things that were in the list. And I think Jin has outlined that procedure pretty well. It's I was basically working with his original tutorial, and there was a few hiccups because, as Sky pointed out, that the API is still very much in development, which threw me for a loop at the beginning because a few things had changed that I didn't know about. But in the long run, it turned out great, because after this initial first attempt at getting the mineral classifications, it turns out there's a property among the many properties in the database for the meteoritical code, which is a code from the Meteorological Society that runs the sort of classification of meteorites for that community. And Pavel added a query ability to look for records in MinDat for materials that had a meteoritical code value, which means they were meteorites. So as I was able to construct a query, again, the long list of fields I was interested in, getting stuff in JSON for things that have a meteoritical code, and that worked great. The only problem is, and this is something that I hope will eventually evolve, is when you run these requests, you can only get 10 responses. So there's about 480 meteoritical codes. So I went and got a cup of coffee while I had ran through the loop to pull them all down. I loaded them in a pandas data frame, which is great. From that, it was really easy to save it out in a CSV file. And with a little bit of Excel manipulation, again, sort of boneheaded, but it works. You can generate SCOS, and that allowed me to construct SCOS, right? And so one thing that's missing here is what kind of URIs to use for these things. But I was using the long IDs to calculate those, and was able to construct the materials, the extraterrestrial materials vocabulary. And so this is an HTML page that spun up from the SCOS that we used. In the meantime, I found out that not all of the MetBull classes are in there. So there's still a bunch of work that needs to be done here. And also some thinking about what the hierarchy of these classifications would look like. But all in all, I've used MinDat for years for a lot of these lithology vocabularies and stuff I'm working on, and it's just a phenomenal resource, and it's really good to see the API coming out. There's some other use cases that I'm interested in, among which for thinking about data entry for sample descriptions in iSamples and Astromaterials. MinDat has, I think it's on the order of 5,000, almost 6,000 minerals listed in it now. And you don't want to construct a pick list for people trying to describe rock specimens with a list of 6,000 possible minerals. So what I've wanted to get for a long time was, okay, well, what are the, let's say, 100 or 200 most commonly occurring minerals? And because you can query MinDat for the number of occurrences of a mineral, The next project I'll try is basically finding what are the most commonly, what are the minerals that have the most occurrences, because these are probably the things you want to show people in a pick list for doing data entry. And there's some other questions that, that also, could be addressed with the data that are there, that would be interesting to experiment. So, looking for rocks that contain kinds of rocks that are likely to contain particular minerals. Geophysicists are interested in rock densities for doing gravity modeling. And so, if you know the modal mineralogy of a rock and Mindat has the densities for the minerals, you can estimate something about what the density of the rock should look like. And then other things about, more related to kind of mineral exploration and stuff. And so, what are minerals that are commonly associated with other minerals? And following on what Sky was saying, I mean, really to me, the evolution of this would be, having URIs for the mineral species that we could dereference to get some kind of RDF representations, but also having the various properties in Mindat using identifiers that we can use for data integration, and linked URIs for the rocks and elements and stuff. And another useful aspect in the API would be, instead of getting, having to create these big field lists for the things you're actually interested in, to have some prepackaged information units that people commonly use. So anyway, that's my wish list. And like I say, Mindat's a great resource, and really enjoyed having an API to be able to access the data. The Slack channel is really useful if you are doing it. The people respond quickly and it's very active. So if you're working with the API and have problems, I highly recommend that. Over to you, Marshall.
Okay. Thanks a lot, Sky. Yeah, we are out of time. So just quickly wrap up. We do have the folder and all the slides and links, GitHub, everything is open. And also we do have the Slack channel. As I mentioned, if you are really seriously interested to continue the usage of this resource, just email me. I can add you into the Slack channel. It's very active in that channel, and there are many. And actually, on the Mindat website, and also there are a lot of other interesting but hidden functions. So we're continually add new features, new functionalities into the website, and then a lot of information is shared in the Slack channel. And also, Sky and Steve both mentioned, because I like the first round of intensive users of the of the API, a lot of challenges, because we're still in the progress. And then it's actually an NSF funded project, as I mentioned. So hopefully by the end of 2024, we will have a very stable version of the API established. So, but so far, many functions and also many fields and parameters, we're still in progress. So, but some of those they are already established. So you're more than welcome to use them and test them. Good, great. That's it. Wrap up the session.